for coming to my channel to actually read about this particular topic called fatigue failure mechanism. Today I'll be talking about this particular topic of fatigue failure mechanisms in materials. My name is Solomon Agbedo. I'm a graduate researcher in Ohio University College of Mechanics, Department of Material Science and Engineering, China. Today, so scientists that makes them to be looking at fatigue as a failure phenomenon. Then we'll also be looking at why we have to study failure in materials. Then we're going to look at the effect of fatigue, then compared to static loading. Then we are going to look at fatigue failure, the causes and the stages of fatigue. So in that place, under this section, we'll be looking at crack initiation, crack growth, and the final fracture of materials or metals. Then we're talking about fatigue. And when we are defining metallic fatigue failure is a failure in metallic components which has to do with the material subjecting to fluctuating loadings, variable loads, the alternating loads, repeated loads, random or cyclic loads. All these are equal to dynamic loads that occur in materials over a long period of time and which occur below the yield strength of that particular material that causes what failure. The places where fatigue are basically common are, you can see bridge. This is a bridge now. It's, engineering infrastructure and automobile cars, engines, and diesel or marine diesel engines too. So these are places where fatigue are basically common. Like this bridge we are seeing here now. This is a Golden Bridge Gate bridge, which on without the moving vehicles, it's on a static loads. So it operates on a static loads, but by the time vehicles start moving on it, it started experiencing dynamic loads, which can cause what fatigue. Like the diesel engine we also have here too, the moving parts too also causes dynamic loads to occur, which can also lead to fatigue. That is the movement of the pieces, then translating energies to the crankshaft, and all these combined together can also lead to fatigue. Similarly, the marine diesel engines too, the movement, the up and downward stroke of the piston also leads to the rotation of the crankshaft, which can also lead to what to dynamic loads that will eventually what cause what fatigue to occur and failure to occur. Then now let's look at the history of fatigue. The first scientist to basically work on fatigue is the Wilhelm August Julius Herbert, was the German mining administrator. He was the first person to propose a theory of fatigue in metals in its time. And after him, some scientists work on fatigue, but they never took it to be so pertinent. So because of that, they were taking it with little with relevance, with little relevance in material design. But the crash of BOAC Flight 781 in 1954 actually attracted scientists, attentions of scientists and researchers to basically look at fatigue as a failure mechanism. So, and this crash took place in Elba Island off the Italian coast, which killed 35 persons on board. I think in the next slide, I will be explaining to us how this the report of the technical report of this flight of BOAC in 1954, according to the way I research it in research. According to reports, it was written, it was reported that the flight took place from Rome and was heading to London, and at a level 1,000 feet, which is a normal culture in avionics. Then the plane was pressurized. So this pressurization led to compression and decompression, the compression and decompression to take place at the fuselage of the aircraft, And this compression and decompression led to what we call cyclic or dynamic loading to take place, and which eventually made one of the windows to crack initiation and propagation that led to fracture on the fuselage, and which eventually led to what? To explosion of the aircraft and killing people, 35 persons on board. So after this crashed, like 3 months later, another crash took place again of the same airline. So definitely this actually caught the attention of scientists to look in depth what was the cause of these failures in 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 this in their products, and they later found out that it has to do with what fatigue, and that is where scientists started looking into fatigue as a mechanism. The another big question we're supposed to ask ourselves is, why do we have to study failure? It has actually been estimated that approximately 90% of metallic failures has to do with what? With fatigue. And once failure occur, it definitely leads to what? To a loss of lives. Then because lives, especially when it occur where lives are involved, so it leads to loss of lives. Then another part is what? It also leads to reduction or stoppage of what? Productions. So which once it happens in production lines, and automatically there will be closure of the production lines and production systems, so which will eventually would have a reciprocating effect in the economic losses. So that is these three important paramount reasons and why failure in materials need to be what? Need to be studied. And now let's look at the effect of fatigue compared to what? To static loading or static failure. In static failure, deformation or yielding occur, which we can see it when failure is occurring, and which engineers can easily take with cognizance and a proactive approach to it. And another thing about static loading is that it actually leads to when materials are exploited at their yield strength too, we can easily see it occurring. So it also leads to warning signs. It can also give us warning signs when it begins to occur. We can see that the material is beginning to plastically deform, which we can easily take proactive measure in order to avert it. So another thing about static loading is that the theory are well understood. We know definitely that if we exploit a material above it or at the yield strength, definitely it's going to be plastically deform, which will eventually leads to failure or fracture of that material. But in fatigue, it's not like that. It's the failure of fatigue is sudden and catastrophic. It's we cannot actually tell when it's going to occur. So that is why fatigue is very very what is the factor of fatigue is has to be very very what taken care of, especially in materials or mechanical designs. And the damage of fatigue is irreversible. We cannot actually reverse the damage caused by fatigue failure. Another thing that is so touching about fatigue is that it's occur below the yield strength of the material. When the material, we believe that the design is that okay, the stress that can basically yield this material is okay, 750 megapascal or gigapascal can yield this material. We found out that okay, we have not actually exploited this material to this strength already, and eventually we found out the material will fail. So it shows that the fatigue has occurred. We cannot authoritatively say until we actually confirm that, which we can trace the cause of such failure to fatigue. Another thing about fatigue is that it is macroscopic and microscopic discontinuities along the surface of the material. So I think when we begin to go to the other slides, I will explain what I meant by macroscopic and microscopic discontinuity. We also go to look at the theory of fatigue is highly complex, because if the theory is well understood now, I believe fatigue would have tried to be prevented not to occur in metallic materials. But because the theory is not still well understood, that is why scientists have not actually come up with a idea on how to totally design against fatigue, because there's no way we can avoid fatigue in metallic component or mechanical designs. So there's no warning signal. It does not show us that it's going to occur. The failure of fatigue occur like a brittle mode. So you will not see it. It will not show you any signal. There's no yielding. There's no plastic deformation. It will just occur catastrophic. Now let's look at the cyclic stresses. Like I defined fatigue to be a failure that has to do with material or metallic components subject to cyclic stresses or cyclic loading. So now the cyclic stresses could be axial stresses, or they could be flexural stresses, which has to do with bending. It could be torsional stresses, which has to do with twisting in the material, or sometimes these stresses could also be in combination. Either two or three of them can be active in materials at the same time. So places where those cyclic stresses are highly paramount are like I told you, the car engine or the diesel engine too, whereby there is rotation of the crankshaft and the gear system. So all this actually leads to cyclic stress, like what we have here now. You can see, like this is also a this I will explain this one too. Then we have another the gear systems too. The content of gear systems can also lead to what? To cyclic stresses. When we mean the stresses are cyclic, we mean that the profile of the stresses is what sinusoidal. You can see how the stresses are alternating from positive phase to negative phase, positive phase to negative phase over a long period of time. That is what we mean by what cyclic stresses. So as you can see, like we have here, okay, let me use this diagram to explain this. This is a car, and this is a automobile engine that has to do with a crankshaft, a connecting rod, and a piston, a crankshaft, and a connecting rod. So when the rotation, let's assume the rotation starts from here and begin to rotate, and come back again to this place, and this is continuous. So when the rotation starts from here, begin to move from here to here, we believe that the stresses that are in this material are SI stresses, which has to do with tension in the crankshaft. So you can see, like we have here, the stresses will be tension, which basically mean they are the positive stresses occurring in this material, which is basically, this is a crankshaft, this which is basically here will be experiencing what? Tensile stresses, which means they are tensional. So you can see it, and this is also an explanation of that too. Then once the rotation reach this particular zone, which we call the neutral zone, we believe that the stresses will migrate from here and come to here at the center. So which basically there is no zero stresses, which is here. That is, the stresses have migrated from here, they are now here, so it will be zero stresses. Then, and when the rotation move be beyond the center point, which is basically here, the part which we are in tension before, begin to experience what? Compression. The stresses will migrate to the down part, which is basically here. So the places which we are in tension before will be in compression. So that is why you can see compression is taking place here. So which is basically the stresses are now here, and it's now along the negative part of what? Of system. So that is what we mean by cyclic stresses. That means it is sinusoidal profile that occur all over a long period of time, which means the stresses are alternating both into positive and negative phase over a long period of time. Once this begin to occur in materials, then we have what we call what? Fatigue. Then we have types of these stresses. Sometimes this we have what we call a reverse stress cycle, which has this particular diagram. We say when we say a reverse stress cycle in fatigue, we say that the stresses, the positive and the negative stresses, or the compression and tension forces, stresses are what are of the of equal, they are opposites. You can see that is what we mean by reverse what stress cycle. So we have what called repeated stress cycle, and in reverse stress cycle, before I forget, reverse stress cycle always starts from the zero origin and to what to increase. We have what we call repeated stress cycle. Under repeated stress cycle, the minimum and the maximum stress are asymmetric to each other, so they are not equal. So, and the stress never originated from what? From zero. So that is what actually leads to what? Repeated stress cycle too. We also have what we call random stress cycle, which are basically experienced in GR systems, so or mechanical systems. So and we have, for us to be able to resolve this dynamic random stress cycle, which has to do with what we call multiple repetition of one part, one phase of this of the stresses. We can actually resolve it into a reverse stress cycle or repeated stress cycle by using rate flow method. And for the scope of this work, that is another aspect of on its own, and we are not going to look at that. The only thing I want us to just understand here is that it's also a type of stress cycle too. There, when we're talking about stresses and stress, cyclic stresses, there are some important parameters and terminology we're supposed to get ourselves abreast with. So like we have here, this is a profile of a cyclic loading system. So we have number one thing we're supposed to understand is what we call mean stresses. What are mean stresses? This is a mean stress, and this is a place where we can locate it basically in a profile. We say mean stress, we say it's defined as the average of the maximum and minimum stress in the cycle, and and we can say that by mathematical representation of that, we can say the mean stress is what the maximum stress, which is this max stress, plus the mean stress, which is this the compressive stress. We sum them together, divide by 2, we can easily get the mean stress in the material. Another thing we're supposed to understand is stress range, which we can represent with sigma r. The stress range, we can define it as a difference between the maximum stress and the minimum stress, which is basically we can locate here. That is this, we subtract the maximum stress from the minimum stress, we can get the stress range of what of the cyclic stress profile. So that this is mathematical representation, that is the sigma r equals to sigma max minus sigma mean. We can easily get the stress range of the profile. Another thing parameter we supposed to address, we supposed to know too, is what the stress amplitude. The stress amplitude, we say that is the max or the mean stress applied to the what or the just half of the what of the range of this range of stress. We can say that mathematically we can say the stress range divided by what by 2, we get the what the stress amplitude. So that is the half of the difference between the max stress and mean stress will give us the stress amplitude. Then we have what we call the stress ratio. The stress ratio can be defined as the ratio between the ratio of the mean stress to max stress. So which basically we can represent with a capital R, and we say the mean stress upon what max stress can give us the stress ratio, which which is which is represented here on the profile. So all these parameters can be seen in the cyclic what stress profile. Let us look at the fatigue failure, the causes and the stages in fatigue. We basically said that the causes of fatigue failure are basically is in stages. Before we can say a material failed under fatigue, we have to look at the failure sequentially in various stages. The first one is what we call crack enucleation or crack initiation, which has to do with which can easily be caused by inclusion or flaws or imperfection or void in materials. There is no particular material that is free of void or that is a perfect ideal material. All materials has flaws or imperfections in them. So all these can easily cause what fatigue, even while those we try to control them during production history or the processing history of the material. During a mechanical assembly too, we can sometimes incorporate all those ones into the materials or into the mechanical system. It will also have what we call localized yielding. Localized yielding can also initiate fatigue, especially when those flaws are there and this material is subjected to cyclic loading. We can actually have what we call localized yielding begin to take place. We also have what we call sleep along boundaries too, can also cause what initiate fatigue, because especially when the 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 there are no inclusion, we try to avert inclusion in the process history of the material, or we try to what design against them. We found out that what during usage of the material or in service, we found that the material will actually when it is subjected to cyclic loading begin to take place. It can lead to what we call slips along the boundaries or the grain boundaries of the material, which will basically leads to what to crack initiation and crack growth. So the next stage of fatigue is called crack propagation or crack growth, which has to do with orderly crack growth or crazing, especially when we're looking at polymers. We say crazing of the material. So we're going to look at that in the other part of the slide. So the final part of fatigue, well, before we can authoritatively say material feed other fatigue, is a fracture that took place in the material. So which has to do with what when the remaining part of the material cannot support the stresses in the material, which will definitely lead to rapid fracture or catastrophic failure of the material. Then we look at stage one, crack initiation of fatigue. So let's look at that. Like I said, there is no ideal material before, and we said that a crack associated with fatigue failure almost always initiated or nucleates on the surface of the component at some point of stress or concentration. Yes, we're going to look at that. Like I said before, that we cannot have an ideal material, and sometimes when we try to avert these voids or imperfection in materials during mechanical assemblies too, maybe you try to put keyways or try the fillet systems, in material can actually cause stress concentration in material, and once those stresses are concentrated and this material is subjected to cyclic loading, we found out that the failure will begin to initiate along the stress concentration points of the material. So this is a shaft too, which has a key way in to connect the pulley to it. And by the time we try to incorporate the two systems together, we found out that and this system is subjected to cyclic loading, crack can easily be initiated along this part of the system. And this is a jar system too. Crack can easily be initiated here because at these points too, we can easily have what we call stress concentration, because these are the places where the stress will be concentrated. We also have word parts too. You can see the places where systems are welded together, structures are welded together. We also have stress concentration at those points too, which can definitely lead to what to fatigue, crack initiation too. So all these are what we call as surface discontinuity I'm talking about in materials. So like I think I did here, I just did a little model in order to simulate what we call stress concentration stress amplifying factor in materials. And this is a particular a component which was subjected to what to tensile stresses. 50,000 newton, which is 50 kilonewton, both on the y-axis opposite to each other. So when this material was pulled in tension, this is the result we had, and we found out that the stresses are basically concentrated at what, at the fillet parts of the what, of the material, which are basically at this joint, at this point. So we can, which we say that the stress that the stress applied are basically equal to the what, to the normal stress of the maximum stress, are basically equal to the normal stress occurring in the material, and the stress concentration or stress concentration what are located here, because this is our places where the stress risers are located in the material. But I tried to incorporate a notch into the system. I found out that the stress concentration migrated to this particular point of the system because of what, there's a stress what concentration, which will basically say that what, that, and that the stress, the maximum stress that are occurring in this material now is as a result of what, this stress concentration that are added here, which has to do with what, this the stress intensity factor, multiply the normal stresses attached to it, which will basically make the the stresses here to be amplified. And when these materials want to fail, the failure will begin to start from here, because these are the places where the stress risers are located. So these are the factors of a stress riser or stress amplifiers in what, in systems. So sorry, excuse me. Yeah, another thing I told you that we have what we call what, yield, local yielding. Once this material begin to experience dynamic loading, I just want to use this diagram to explain something to you. Once it begin to experience what, tension or dynamic loading, or under tension, you found out that what, there's what we call local yielding begin to take place. Those stress concentration causes local yielding to take place, whereby the other parts of the parent material begin to experience normal stresses but related in that particular area, and which will lead to localized yielding, and automatically will lead to what, so I explained, I put here that that's that same couple I simulated here, and I tried to pull it in tension to see the deformation, how the deformation is going to take place. Like, let me play this video for you to see. Like you can see now, when I try to pull the couple apart, you found out that the stress, sorry, let me go back again. I want you to see that the stresses, the crack can easily initiated from here, which has to concentration. So initially when we simulated this particular couple, we found out that the stresses were basically concentrated at the fillet parts of this system, which has to do with the discontinued parts of the system. But when now we now try to incorporate a notch to it, you found out all the stresses migrated to the notch, because the notch is acting as a stress riser. Now let's look at crack crack and nucleation continue. Like I also told you before, that sometimes we may not have okay, let me go to the next slide to explain this to you. We may not have a crack initiation, we may not have inclusion or imperfection in the material. Basically, sometimes we have what we call persistent slip bands, which can also lead to crack initiation in the material. Like I put here, say generally accepted that I be explained that mechanisms of metal fatigue is based on dislocation theory. And basically, the theory says that the atomic arrangement in crystals of a metal is what is imperfect, and contains what numerous missing atoms, and the missing atoms create what gaps, which causes what massive stress risers too. So those dislocations that occur in material, which can basically makes material to be plastically deformed, causes stress risers or stress amplifier in the materials too, which will definitely leads to what we call persistent slip bands to take place, and which will definitely lead to surface discontinuity. And this persistent slip band system induce slip planes and result in what intrusion and extrusion along the surface of the material, and which will definitely lead to slip not what doing. We have what we call what microcracks begin to what to emanate from the what from the slip band system, and which will lead to what we call uh, crack propagation. And crack propagation will definitely lead to what rapid fracture, and which we say that the material has failed under what fatigue. Like we say here, let me explain with these diagrams that are here. We have what we call dynamic loading. Like we have here, this is a cyclic or dynamic loading. As it begins to occur in this particular material, then the dislocations material we want to experience what micro what plasticity. And this microplasticity, which basically start at the surface of the material, and are due to sometimes due to scratches that are on the surface of the material, or basically they may not be scratches. So when these dynamic loads take place over a long period of time, this will lead to what this microplasticity to start to be taking place. And this microplasticity will definitely lead to what to slip to occur at the surface, and which will make the material to what you can see here. As the stress increases, then we definitely will have what we call more slip bands and begin to incorporate into the system. These are the slip bands, you can see them here. These are the slip bands. Then as you begin to increase the system, the stresses over a long period of time, more slip bands are increasing, and by so doing you begin to see that what there will be a surface discontinuity. You can see the surface be what uniform. At this point where the slip bands are now increased, you can see that what there is a discontinuity at the surface of the material. And once this continue to take place too, we begin to see more slip bands begin to take place, and you can see there's a protrusion coming from the surface of the of the surface of the material. By so doing, we begin to have what we call surface intrusion and surface what extrusion. So these are the intrusion and extrusion in the system. And we also use a micrograph to explain this to us. I think let me put the micrographs here. Like we have here, you can see this is a micrograph showing an intrusion and extrusion taking place. This is an extrusion, this is an extrusion at the surface of the material, and this is an intrusion. And these are dislocations occurring in the material. These are dislocations. These dislocations leads to what this slip bands to take place, and like I explained in the previous slide. And by so doing, and this is another micrograph too, which is showing an SEM showing what slip bands. You can see this is a PBS, and you can see now this particular part is called intrusion. The part that go inside is an intrusion, then the part that protruded out is called an extrusion. So all these can definitely, and these are occurring at the microscopic level. All this begins to occur will lead to micro cracks to be initiated. And when this particular such material is subjected to cyclic loading over a long period of time, you begin to see uh, uh, cracks to begins to propagate. So this is also this is an inclusion. This is an inclusion in materials which can also cause fatigue too. This is due to imperfection in the material. Those ones, these are particles in materials, and which can also cause what stress field to start to take place here. And when these materials subjected to cyclic loading over a long period of time, this stress field will definitely lead to local yielding, which can initiate cracks, and the cracks will begin to grow and propagate to final fracture, which can cause what fatigue. Okay. Okay, there's you can basically, I think there's a particular resource online in journal published by Veronica. You can go online to search for this particular paper. It's actually explain a lot about surface intrusion and extrusion, and how dislocations causes what fatigue in materials. You can Google that, and you are going to have a lot of knowledge about that too. Now let's go to stage 2 fatigue, which has to do with crack propagation and crack growth. So, like we said before, that repeat like the first stage, when those cracks are initiated, for those cracks to propagate or try to grow, there's another word and another mechanisms that are associated with them. The first part of it is what we call what opening, crack opening, which has to do with repeated blotting and sharpening of the cracks, will make the cracks to what to propagate and grow. The first part is what we call crack opening or other tensile loading. When those cracks begin to what to be under tension, also when the material begin to experience tension, we begin to have what we call crack, and we begin to what the system, the slip system begin to what to, you can see the slip bands develops along the crack tips, which is basically here. You can see the crack tips and the slip system begin to increase, and then when this with further loading, the crack tips begin to blot. So once you begin to open more, you begin to open the pull the system apart under tension, the crack tip will begin to blunt, which is here. And under compression, you try to compress it again, which has to do with the dynamic loading. You found out that what the cracks still begin to sharpen, and the slip bands that we are projecting from the surface of the cracks will begin to reverse again and back to the surface. All this, makes the cracks to grow and begin to tear more and more and more. Then you see the slip bands begin to reverse back again, and those ones that will go in begin to go out. So all these crack uh, blotting and sharpening causes beach markings. Yeah, exactly. Which we call beach marking striations. Microscopically we call them striations, or we call them under a microscopy when we can see them with our eyes, which we can call them what beach markings. So, and for one beach mark to occur in a material, which is a projection from here to here, a projection from here to here, is as a result of once complete cyclic loading, or when a particular machine work over an operation over a long period of time. When it completes a single operation over a long period of time, that is when a beach mark will occur in material. Then stage 2 continues. So let's talk about this beach mark. Like I said, that the region of the fracture surface that formed during the cracks propagation step may be characterized by two types of marks, which are called beach marks or striation. So when you look at this particular surface of a material fracture under fatigue, you can see the ridges. These ridges are called what? Beach marks, especially when you can see it with your naked eyes, or you don't need an aid, or you don't need aid systems to look at them. We say it's a beach mark. This is it. It's a beach mark. But when you require microscopes to look at them, we say they are striations. So the marking are found for a component that experience what? An interruption during the crack propagation stage. An example is a machine that operates only during normal working shift hours. Like I said before, that when a machine work over a long period of time for a complete operation, it will lead to to a single beach mark, which can occur. So fatigue loading and which definitely occur for a very long period of time. So that is when we can say that what a material fail under what fatigue. This is a particular crash shaft. This is a particular crash shaft. Here you can see the crash shaft. I will believe that the rotation of the crash shaft is in this direction, and the crack actually initiated or originated from this place. And when the crack originated from this place, then the crack begin to propagate towards this place, and finally we can say that final fracture took place at this particular zone. So we in the other part on that slide, I will explain to us how final fracture and rapid fracture we can know places where crack initiated from in materials. The fatigue crack growth rate, there's for us to be able to understand the science behind this crack growth, we need to understand a fundamental theory called crack growth rate. But this one we're not supposed to study. We're supposed to study it under what fracture mechanics of materials. From our previous knowledge of fracture, I'm going to borrow the knowledge from fracture mechanics. From our previous knowledge of fracture mechanics, we are exposed to crack growth rates. The fatigue crack growth rate helps us to understand the knowledge of fatigue what process. Like we say, crack growth rate can also be used to predict materials fracture toughness of the material too. So then we also look at how do we go about this? We say a sample is subjected to a fixed stress or strain amplitude at a specific what stress ratio, and finally the crack length C is what is measured microscopically. Then the plot result of crack length versus what number of stress cycle to failure. We definitely will show the crack growth rate. So diagrammatically, this is what we are talking about. When you pick a particular sample of material, you design a material, you subject it to a fixed stress, for over a long period of time, definitely the stress will definitely would cause what the crack in the material to grow. And once you measure the length of the growth, which is we can call C, which we represented as or denoted as C, then over the number of cycle the material was subjected to before failure, then we plot them together, we can get a profile like this. Then the differentiation of this particular curve is the slope of the curve is called the crack growth rate. We call it, which is the slope of the curve. And we said that the stress ratio, like I have explained what the meaning of stress ratio in the first part of this slide. The stress ratio, as the stress ratio is increasing in the material, definitely the crack growth rate is also increasing. That is what this profile is telling us. And the number of stress cycle to failure will decrease. So it's increasing. The crack growth rate is also increasing, and the number of cycle to failure is definitely decreasing. The crack growth rate, the scientists that actually work on this particular area on how to relate this crack growth rate with a stress intensity factor is called Paris is called Paris law. So he actually did is a fracture mechanics engineer, a scientist who did a lot of works in in fracture mechanics on how to relate a crack growth rate with a stress intensity factor. From Paris law in 1961, based on the fracture mechanics, they actually suggested that the rate of a crack growth can be characterized using the stress intensity factor of the material. So like we have here, you can see these are the various stages that the previous crack growth rate, which was a profile of that graph. If we plot it with the stress intensity factor of the material, you're going to have a particular profile that looks like this. And the slope say that is the C all over the capital N is proportional to the what, to a range of stress intensity factor raised to the power of m, where m is what empirical what constant between 2 and 7, which we can really choose, and a is a constant that depends on the materials and the stress ratio of the material, so that we are actually what investigating. That the explanation of the crack growth rate and versus stress intensity factor, like we have here, let me explain the profile to you. You can see that what the stress intensity factor is divided into 3 regions, which is basically was region 1, which is this one, then region 2, which is this place, and region 3, which is this particular place. In region 1, we say that at a very low stress range, stress intensity, stress intensity factor range, we have what we call what it's quite of low at this particular place. The stress intensity factor range is very low at stage 1, which is basically here. You can see basically we're starting from 1 to 4. Then another thing is there is a what there's the stress intensity factor. There's a particular threshold of stress intensity factor that when a material that the crack in the material is below this stress intensity factor, there is no amount of cycle that can cause what fatigue, and that material can never fail that fatigue. That is, if the cracklet is below the stress intensity factor, which is between this particular region to this particular region in the material, there is no amount of cycle that can cause fatigue in that material, which all these are happening in region 1 of the material. So another thing we're supposed to understand is that the crack growth rate is sensitive to what? To the stress ratio of the material at this stage 1. It's only this crack growth rate is very sensitive to what? To the stress ratio of the material. Then here at this particular point, you will not see uh, uh, no striation or no stress or fracture surface at the surface of the what, of the material. You will not see striation at the surface of the fracture surface, where especially at this place where crack initiated, which is the region 1 of the what, of the of the crack growth rate. Then region 2, in region 2, which is this particular place, we said that the crack is relationship here, which means the Paris law, it become what is becoming linear, and which the crack depends on the power factor of what, of m, which you can see from here. And that is why when you take the slope of this particular, you can easily measure the slope of this particular place, because it has a linear behavior here, which has to do depend on this power of what, of this power of m. Another thing we're supposed to understand in this region too is that in this region, we have less sensitivity to the stress ratio. The stress ratio is not basically prominent in this particular region of what, of the crack growth rate versus stress intensity factor profile. Then the at this particular region, that is where we have what we call striation. You can easily see striations begin to occur in material here at this particular region too. So when striations occur, you know that the material has passed the threshold stress intensity factor, and it's now what, in region 2 of the material, in region 2 of the profile. Then in region 3, we have the crack growth rate is also sensitive to what, to R2. You can see which is stress ratio. You can see the profile begin to what, to curve again, because we now begin to have a curve profile, or like here we have a linear profile in stage 1, or in region 1, in region 2. So another thing is that what, there is no striation too at this particular part where the material fracture. So at this part too where the material fracture, you will not see striation. Striation will not occur in the material. These are various this is an aluminium. Okay, this data, I got this data from NASA TN between 1969. Then this is a material that is subjected to different a different stress ratio of 0, then 0.2, 0.3. You can see as the stress ratio is increasing, then the stress intensity factor, the stress intensity factor is what is definitely what decreasing. So we can say from here that the stress ratio increases, then there is a shift in the stress intensity factor, and the threshold of the threshold stress intensity factor range will definitely shift to, so decreases also shift towards the left side too. So another thing we're supposed to understand from this place is that the crack growth rate increases too. Growth rate also increases too. Then from this profile too, we also know that the fracture toughness of the material decreases too. As we increase the stress intensity factor, you can see this fracture toughness decreases. So there's something I'm supposed to explain to you in the previous chapter. So like here, the particular place, why we say that the stress intensity factor, the crack growth rate, we can actually use it to determine the fracture toughness of the material is this. Especially when you, after you have actually exploited the material all through this profile to this particular final fracture point, which is this particular place, we can see from here that the ultimate fracture that took place in the material occur at this particular place when the maximum stress intensity factor is equal to the fracture toughness of the material. So when immediately the fracture toughness of the material equal to the maximum stress intensity factor range, you find out that the material will definitely fracture. At that particular place, at that particular point, you find out that the strength of the material will not be able to withstand the cyclic stresses the material. I forgot to explain to you. So the third part, the stage 3 crack fatigue is final fracture of the material. So, and like I said that there is an uncontrollable and rapid extension of the crack within the component, especially when it has propagated. Like you can see, this is and the stress intensity factor is equal to what the fracture toughness of the material. In stage 3 of the fatigue, we begin to see that there is an uncontrollable extension of the crack within the component, at stage 3 to the stress intensity factor is equal to the fracture toughness of the material, and which we have already explained from the profile of crack growth rate versus stress intensity factor according to Paris law. You can see from this fracture surface of a material, you can see at this particular place, like I told you, there is no striation occurring at the surface of the material. So you can see crack initiated from this particular place, and finally this is the place where the crack, there is what we call region of rapid crack propagation or rapid failure occur here, and finally the fracture took place at this particular zone. You can see there's no striation here. How do we know that a material in the crack initiated from this particular place? Especially when the material is experiencing tension, we found out that there's a tearing which is basically nearly 45 degree to the surface, 45 degree to the surface of the material. So at that particular place, we can easily identify that the crack initiated from that particular surface of the material. As the crack begin to propagate, then definitely the fatigue is liable to occur, which is basically the stage which is we call here the stage 1 fatigue, stage 2 fatigue, and finally the final stage of the fatigue is basically this particular place where the fracture is going to take place. And the video, let's do a conclusion, a review of what we've learned so far. And in the course of this presentation, I was able to let us know the meaning of fatigue. I was able to let us know the meaning of fatigue. Then we also look at the history of fatigue too. We also talk about the history of fatigue and why scientists decided to take cognizance view of fatigue, and we'll look at how fatigue is being initiated in materials, fatigue initiation, crack growth, fatigue, look at fatigue, how fatigue starts, then how we can authoritatively say a material feed under fatigue. Then finally, we also look at the features of materials that feed under fatigue. We also look at the features of materials that feed under fatigue, and finally, we look at crack growth rate and how we can authoritatively use it to ascertain the fracture toughness of material. Crack growth rate, crack growth rate. Then finally, we look at the final fracture of a material that feed under fatigue. So thank you for watching. In the next module, I will be talking about how we can design against fatigue using a theoretical method. How we can actually design, then comparing our results with experimental data. In case we don't want to perform experiments or fatigue tests, we can use theoretical means and some relevant models to work to design against fatigue, and then using those models and the results to minimize the occurrence of fatigue in mechanical designs and materials.